Okay, in this podcast we're going to talk about organic chemistry. If you were to go to college and major in chemistry, your first year is general chem, your second year is organic chem. Organic chem is the study of carbon-containing compounds, and it's a really important part of chemistry because if you look at there are thousands of new compounds that are synthesized every year, and about 90% of those are going to be organic. So a lot more stuff really happens with organic chemistry than with inorganic chemistry in the real world. So it's a really important piece of chemistry, and was actually what I fell in love with and caused me to switch my major from bio to chem when I was a sophomore in college. Now, a lot of people think organic is really tough, and it can be the course that causes people to switch from things like pre-med or even being a chem major because people, it's the weed 'em out course. I didn't find it that way. I found it to be probably easier than Chem 1, probably because of the way my brain worked, but so you might have I think a lot of it depends on who's teaching it, but I had a great professor. All right, here we go. All right, so it's organic chemistry is the chemistry of carbon compounds. When it was named organic chemistry, people used to believe that it would only life processes produced carbon-containing compounds, that you couldn't synthesize them, and that was actually proven wrong in the early 1800s. A lot of those carbon-containing compounds are produced today. Carbon, one of the nice things about carbon, has this ability to make really long chains, and those long chains have nice properties for a variety of functions, both in terms of consumer products, but also in your body. So if it wasn't for this ability to have these long chains, we wouldn't be able to live. So there are basically three types of hybridization on carbon compounds, depending on whether or not they have a single bond, which makes them sp3 hybridized, a double bond, which makes them sp2 hybridized, or a triple bond, which would make them sp3 hybridized. There are four types of hydrocarbons. Again, alkanes are one type where you have all single carbon to carbon bonds. In alkenes, you have double bonds. In alkynes, you have at least one triple bond. And aromatic hydrocarbons are where you have a cyclic structure. Alright, so alkanes only contain single bonds. They are known as saturated hydrocarbons, which means they have as many hydrogens as is possible. So if you have heard that you shouldn't eat a lot of saturated fat, that means you shouldn't eat carbon-containing compounds that have all single bonds, because if they have single bonds, they can hold more hydrogens and they're completely saturated. So this is what a typical Lewis structure for an alkane would look like. They're called structural formulas, but they're often not convenient enough, so a lot of times these condensed formulas are used. But they'll be shown either way. And depending on the length of the chain, you get more or less van der Waals forces. And as the number of van der Waals forces goes up, so does the boiling point. And these are prefixes that are used to name organic compounds, and the names are dependent on the number of carbons in the chain. So the prefixes are here: meth, eth, prop, but, pent, hex, hept, oct, non, dec. Many of these are the same ones we use for naming molecular compounds. Meth, eth, prop, and but are different. It was, if you remember, it's mono, di, tri, tetra. But they're all pretty much the same after that: penta, hexa, hepta. Alright, so you probably know most of them, and the others you'll learn pretty quickly. Alright, so we've already said carbons and alkanes are all sp3 hybridized, which means they have bond angles of 109.5. They're all tetrahedrons. There are only sigma bonds in alkanes, which makes sense because if it was a double bond, they would have both sigma and pi, but they're all single bonds, so they're all sigma bonds. There is free rotation about the carbon-carbon bond, so this molecule can actually move around. Now, there's a lot of one of the things you need to know about in organic chemistry is isomers, and isomers are anytime you have the same formula, but the atoms are bonded in different orders. So a lot of times in organic chemistry, you'll have a formula for something, and in fact, you have two different compounds because of the way that the bonds are come together. So, for instance, this pentane here is a linear chain, but you can also have this pentane here where one of the carbons is on a branch. And those are called isomers. Same composition, different bonds. And there's a couple different types of isomers we'll talk about. Most of what you're going to do for this unit is learn how to name stuff. So there are three parts to a name of an organic compound. The base is based on how many carbons are in the chain. The suffix tells us what type of compound it is, whether it's an alkane, ene, or ine, depending on whether it's single, double, or triple bond. And then the prefix tells us what groups are attached to the chain. Okay, so when you want to name a compound, first thing you have to do is find the longest chain in the molecule. And if you look at this molecule here, people will look at this and say, well, it's a 4-carbon chain, the longest chain, but in fact it continues up here in this way, so it's a 6-carbon chain. And if it's a 6-carbon chain, it's going to be called hex. So this would be a hexane. So in this case, we have if we consider this to be the chain, on the second carbon we have a methyl group. Okay, so we always number the chain from the end nearest where the first attachment is or substituent is. So we start numbering the carbons on this side because the methyl group here comes early, comes closer here, as opposed to if we named it this way. We're going to call it 1,2-methyl hexane. Okay? If we were to number this way, we'd call it 1, 2, 3, 4, 5-methyl hexane. You want the number on the group here to be the lowest possible. And the side chains we call methyl, ethyl, propyl, butyl, again, based on how many carbons they have. So we list this as substituents as a prefix along with the numbers of the carbon to which they are attached, which is why this is a 1,2-methyl hexane. If there's more than one type of substituent in a molecule, we list them alphabetical. So here we have 1, 2, 3 methyl groups, and we have an ethyl group because it's got 2 carbons. And because ethyl comes before methyl, we start the chain, numbering the chain in the place that makes the ethyl the closest, or the lowest number. So it's a 3 ethyl, 1, 2, 3 ethyl, 2 on carbon 2, 4, and 5 we have methyl, so we have 2, 4, 5 trimethyl, and the longest chain is 1, 2, 3, 4, 5, 6, 7 carbons. Carbon can also form ring structures. 5 and 6 membered rings are the most stable. Okay. All right. Alkanes are relatively unreactive because of the sigma bonds. Oops, let's go back. And they tend to be used as nonpolar solvents. So think about methane, propane, butane. Okay, and then there are alkenes. An alkene contains at least one carbon-carbon double bond. It can be a really long chain of single bonds and have one double bond between the two carbons, and it's going to be called an alkene. They are unsaturated. So the carbon here has only 2 hydrogens as opposed to 3, which you'd have if you had a single bond. Okay. Unlike alkenes with double bonds can't rotate freely about the carbon bond. The side-to-side overlap in the pi bond, right, because it's a double bond, makes the rotation impossible. And this creates what's called geometric isomers. So this is isomers that have, in fact, the same composition, also the same groups attached, but they are attached in different ways. So here is this unmovable bond, right? There can't be any rotation around here. So I've got this ethyl group and methyl group both on the same side of the carbons, and on this one I have this ethyl and this methyl on opposite sides of the carbon-carbon double bond. Whenever things are on the same side, we call them, same side of the carbon bond, we call them cis, and when they are on opposite side, we call them trans. Okay, so same exact group, same exact composition. These are geometric or structural isomers, sometimes called stereoisomers. Okay, so the property of alkenes, structure affects their physical properties. So depending on whether they've got, again, these are all isomers here. They all have the same formula, and what you see is some differences in the boiling point. So you actually see different physical properties. They're not wildly different, but they are different. Alkenes are numbered so that the double bond gets the smallest possible number. So here we have a bunch of carbon-carbon bonds. One of them is a double bond. So we name this, number them so that we indicate where the double bond is, and we make the double bond the smallest possible number. So this is 1 pentene as opposed to 1, 2, 3, 4, 5, or as opposed to 4 pentene. Okay. Again, cis chains have the carbons on the same side of the molecule, and trans have them on opposite sides. One reaction of alkenes is known as an addition reaction, and what happens is this double bond gets broken and something will attach to each of the carbons. So 1 pi bond and 1 sigma bond are replaced by 2 sigma bonds, and therefore energy is lost. It's exothermic. This is favorable from a spontaneity standpoint. It's a 2-step mechanism. Not that important to know these mechanisms. You'll learn all about this when you get to organic chem. Okay, then we have alkynes. So we've had alkanes, which are single bonds, alkenes, which are double bonds, and now we have alkynes, which are triple bonds. Alright, so alkynes contain at least 1 carbon-carbon triple bond. The carbon in the triple bond are sp hybridized, and they are linear. They are also, of course, unsaturated. We name alkynes in the same way as we name alkenes, with the exception that the word ends in "ine" as opposed to "ene." Alkynes undergo many of the same reactions that alkenes do, and the impetus for reaction is replacement of the sigma bond, the pi bonds with sigma bonds, which are more stable. Then we have the aromatic hydrocarbons. We've talked a few times about benzene. And there's a p orbital on each atom. The molecule is planar. So many of the aromatic hydrocarbons are known by their common names as opposed to their IUPAC names. Things like benzene and toluene, pyrene, Okay, so in aromatic compounds, unlike alkenes and alkynes, each pair of pi electrons does not sit between two atoms. So we end up with 1, 2, 3, 4, 5 pi bonds on this 6-member ring. And as we talked about when we talked about bonding, the electrons end up becoming delocalized, and you end up with basically a circle of electrons above and below the plane. And it makes them very stable. Aromatics do not undergo substitution reactions or addition reactions. They undergo substitution again instead, where hydrogens get replaced by something. Don't really at this point need to know this ortho, meta, para stuff, but they can have the same groups, just different locations on the chain. The reactions of aromatic hydrocarbons often require a catalyst, because they're so stable, they're not going to easily react. When you get into functional groups is where the number and types of organic compounds you have can really literally explode, because you just change a group that's on the chain and you completely change the properties of that carbon chain or that organic molecule. So if you have a carbon chain that has a OH coming off of it, you have an alcohol. And we call those, if it's got 3 carbons, it'd be propanol, or we also call it propyl alcohol. If there were only 2 carbons and it had an OH, we'd call it ethanol or ethyl alcohol. Alright, ethers tend to be quite unreactive. Ethers are where there's a carbon-oxygen-carbon in the chain. They are pretty unreactive. We have carbonyl groups, and a carbonyl group is where you have a carbon with a double-bonded oxygen attached to it. And there's lots of variations of organic compounds that have carbonyls in them. An aldehyde is a carbonyl where you have an oxygen, double-bonded oxygen, and a hydrogen. Things like formaldehyde. In ketones, you have a double-bonded oxygen, and the carbon is attached to other carbons, and that makes ketones like acetone. Acids are a carbon with a double-bonded oxygen and an OH. I used to say this to my kids: if you had a formula for an acid and it ended in a Q, you have a C double bond O OH, and that's a carboxylic acid. They tend to taste tart, and they are weak acids. Esters are products of carboxylic acids and alcohol, so they're a C with a double bonded oxygen, and that C is also attached to another O, which is attached to a carbon. So just one specific type of hydrocarbon. They're found in fruits and perfumes. And then there's amides, and amides always have a nitrogen in them. So here it has a carbon with double bonded oxygen with a nitrogen, and they tend to be really kind of stinky. They are anything with the nitrogen can be unpleasant odors. So amines also have nitrogens, and they have strong unpleasant odors. So it's carbon with a nitrogen attached. And that's going to do it.